Okay, so now we're going to look at a reaction that I did in the laboratory, and this is in a fume hood because it gives off a very noxious gas called NO. And I'm going to react a penny, which has copper in it. And the reaction is copper plus concentrated nitric acid, which is 15 molar nitric acid. So copper plus nitrate acid gives you copper 2 plus. So the copper is going to dissolve. The penny will dissolve, and it produces NO. Now the NO rapidly reacts with oxygen in the atmosphere, O2, producing NO2, according to the lower reaction. Now what I'm doing here is capping the top of the flask so that most of the NO, which is now NO2, comes out the sidearm. And from the sidearm, I'm attaching a syringe to put some of the, what is now NO2, in the syringe. Now, of course, I'm doing this in the fume hood. You can see I'm wearing gloves, and I'm wearing a lab coat, and the surface, the bench top, is relatively clean. There is some clutter in there, but we do our best. Okay, so now I'm taking the cap off. I've gotten my syringe full of NO2, and you can see that it's boiling and giving off gas. The reaction is quite exothermic and happening rather vigorously. So NO2 is a very interesting gas. It forms an equilibrium with N2O4, and that equilibrium is dependent on temperature. As you raise the temperature, you favor more NO2. You can see the NO2 is the higher temperature form, the dark brown, and the N2O4 is colorless, and it favors the lower temperatures. Okay, so I'm going to work a problem using the NO2, N2O4 equilibrium. So here we have 2 NO2, and it's a gas, and it is in equilibrium with N2O4, which is also a gas. And remember, this is brown, and this is colorless. And recall how the position of the equilibrium is dependent on the temperature. We can shift the equilibrium position more to the left under high temperature, or we can shift it more to the right under conditions of low temperature. And so let's do that quantitatively by showing the delta G of the reaction at two different temperatures. Let's compare it at 298 K, room temperature, and 273 K, that of freezing water. Okay, and we're going to use our favorite equation here, which is delta G of reaction equals delta H of reaction minus T delta S of reaction. And the data we are given is that the delta H of reaction equals minus 57.2 kilojoules, and the delta S of reaction equals minus 176.0 joules per K. Now let's just write the reaction again and we can understand why this is the case. We've got 2 moles of gas going to 1 mole of gas. Okay? And so this is going to be entropy change of negative because the system is starting with more chaos and going to a more ordered outcome. And then it's also exothermic, the forming together of 2 NO2s to make one N2O4 is an exothermic reaction. So this is an NO2 where that's an N, this is an O and an O, and they form together one N2O4 molecule. So the N2O4 is called a dimer of an NO2 molecule. Okay, now let's go ahead and calculate delta G of reaction. Okay, and so that is going to be equal to delta G of reaction is going to be equal to delta H, which is minus 57.2 kilojoules, minus the temperature, 298 K, times the entropy change, which is 0.176 kilojoules per K. And so then doing the math, we get minus 4.75 kilojoules. And so this is spontaneous reaction. NO2 is favored to form N2O4 at 298 K. All right, so let's do this at a different temperature now. This will be delta G of reaction at 273 K. And if you remember the picture, the N2O4 was favored at lower temperature. So we're going to do the same calculation at a new temperature, and in order to do this, we have to assume that delta H and delta S are temperature independent, which is a pretty good assumption. So we will have minus 57.2 kilojoules minus 273 K times, sorry, this is a minus sign up here, minus 0.176 kilojoules per K, and that comes out to minus 9.152 kilojoules. So what we've seen now is that since this number is more negative than the minus 4.75, we can say that the reaction is more spontaneous at low T. Okay, you can hear my son playing the saxophone in the background there. Why is it more spontaneous at low T? Okay, so 2NO2 gas goes to N2O4 gas. Since delta S is negative, lower temperature minimizes the minus T delta S term. And since it's a minus T delta S and delta S is negative, then this whole term becomes positive, and that works against spontaneity, or a negative delta G. Okay, now in addition to calculating the delta G, the free energy change at two different temperatures, we can also calculate the equilibrium constant. What about K EQ? Okay, well, we have an equation for that, and that is delta G0 equals minus RT ln of K. Or another way to write that is that K equals E to the minus delta G over RT. And so K then at 298 degrees Kelvin equals the value of delta G at that temperature, which was E to the minus 4750 divided by, this is in joules, divided by the gas constant, 8.314 joule per mole K, times the temperature on the denominator, which is 298 K. And so when we do the math here, we come up with a value of 6.8. okay, which is greater than 1. And that means the reaction is product, which is N2O4, favored. Okay, now if we want to calculate K at a different temperature, 273, we have to use the new delta G for that temperature, which is minus 9152 joules. Now notice it's e to the minus 9152 joules, so those two minus signs often confuse people. 8.314 and 273 for the temperature. Okay, and this equals 56.4. So notice once again that the equilibrium constant at the lower temperature is greater than the equilibrium constant at the higher temperature, meaning that low temperature favors the products. Low T favors products, and that's because delta S is negative.